begin. Our next speaker is Laurence. Pronounce your last name?
Wijaya.
Wijaya, who
Yes.
talks on polynomial corners over finite fields. Please.
Yes, thank you for the introduction. So, one of the basic theorem in additive combinatorics concerns about the existence of linear patterns in dense sets of integers. So, one of the earliest result on this phenomenon is due to Klaus-Roth in 1953. So, the theorem is like this. So, let R sub 3n denote the cardinality of the largest subset of 1 up to capital N without non-trivial arithmetic progressions of length 3. So I will shorten it by just 3AP. Then we have that R3 of n is bounded above by some constant times capital N divided by log n. So maybe if you know this theorem, this is not what you've usually heard. Maybe some people heard that if we have a dense subset of integers, so the notion of density is using lim sub usually. Then we have that A contains non-trivial 3AP. So I think this notion has been mentioned in several few days ago. So I will also mention in the quantitative setting, now this bound has been improved several times. And the best known bound now is due to Ruscio Ragavan around 3 or 4 months ago. So he showed that R3 of n is bounded above by some constant times capital N divided by some exponential of log n to the 1/6. So this improvement first is due to Kelly-Meka, who showed that the result is true if we change 1/6 to 1/12. And then Bloom-Sisas and Ragavan improve it. So this is the best known bound now. Okay. So there are several directions from here that one can consider. So let me just mention 3 important directions one can take from the Roth theorem. So the most standard one, or the most natural one, is to consider longer progressions. And this is first done by Samredi in 1975. So if we have a quite dense subset of integers, then we have that set contains arbitrarily long arithmetic progression. Okay, so another thing is to change the linear pattern to polynomial pattern. So this is a bit unnatural direction to take, but people have been considering it in the past few years. So it's an active result to see what is the quantitative bound for a set that contains such polynomial pattern. So we change x plus z, x plus 2z, which is 3AP, to x, x plus q1z, x plus q2 of z for some 2 non-constant polynomials q1 and q2. And let's say we have the coefficients are in natural numbers. And then the last direction that I want to say is to consider the pattern in higher dimensional. So for example, instead of considering x, x plus z, x plus 2z in the subset of natural numbers, now we can go to a grid in N2, in N square, and one can consider a density of subset that contains the following pattern. So x, y, x plus z, y, and x, y plus z. And this pattern will be called linear corner. And then you can combine these 3 directions in the way you want. So in my talk, I will focus in the last 2 directions. So I will combine the polynomial patterns and the corner patterns. So we'll call it polynomial patterns. But before discussing that, I will consider first the polynomial progression. So in the polynomial progression, one cannot take arbitrary polynomial in this case. So the reason for this is we have the following example. So consider x, x plus y squared plus 1, and x plus 2 times y squared plus 1. And then consider the subset of natural numbers. Say every positive integer that is divisible by 3. So clearly we have the density of this set is 1/3 in the set of natural numbers. But this set cannot contain this polynomial pattern. So the reason is quite trivial. So one can see if you take x to be congruent 0 mod 3, then x plus y squared plus 1 should be either 1 or 2 mod 3. And similar for x plus 2 times y squared plus 1. Okay. So that means that we don't have the root theorem in this polynomial pattern. And then one can consider similar obstruction if we consider the polynomial corners. So you can take the same polynomial or modification of this polynomial such that you can take a dense subset of n square, but then that dense subset does not contain the following polynomial pattern. Okay, so but if we don't have such obstruction, so and if we consider Q1 equals to Q2, we have the following result by combining the result of Kravitz-Kukalang with the result of Geberliu, Lovett, Ostuni, and Savny. So the result is as follows. So let's say we have A to be subset of 1 up to n squared. Oops, sorry. And then suppose that this subset does not contain the following pattern: x comma y, x plus q of z comma y, and x comma y plus q of z, where q is polynomial in z, but with coefficients in natural numbers. And say that this polynomial is non-constant and having a simple integer root. So again, this is to avoid the obstruction that we had previously. Then we have that the size of this set should be bounded both by some constant times n squared divided by exponent of some power of log n. And this power is small, so this power should be less than 1. Okay, so the reason I mentioned this is the improvement because in the original paper of Kravitz-Kukalang, they show it the denominator is triple log n to some power. But then because their paper appeared in arXiv in 2024, and then there is improvement on the set that does not contain linear corner by these 5 people just 1 year ago. So we can improve it to get this following bound. Okay, so what happens if Q1 is not equal to Q2? So in this case, not much is known. So one of the known cases is due to Pelus, Prendiville, and Shaw in 2024. So let the notation be as before. So let A be subset of 1 up to n square that does not contain the following pattern: x comma y, x plus z comma y, and x comma y plus z square. Then the size of A is bounded both by some constant times n square divided by some power of log n. And then for other polynomial patterns, I think this one is typo, should be Q1 is not equal to Q2. So yeah, for other patterns, you can adapt their arguments, but I don't think it's convenient, and I don't think you get the as strong result as this bound. Okay. So our main result is to consider the bound of the subset not containing the following pattern. So similar pattern as in Kravitz, Kuka, and Leng, but we consider over FP. So clearly, usually in FP, we have a better bound. So we want to know whether we get really better bound compared to the integer case. Yeah, although the model over FP, usually the method does not carry on through the integers, but it's still interesting case to consider in. So again, this bound also appear as a result of the 5 people that I mentioned. So Geberliu, Lovett, Ostuni, and Savny showed that if we have finite abelian group G and A subset G times G without linear corner, then the size of A is bounded by some constant times size of G square divided by exponent of some power of log of size of G. So in this case, the power is 1 over 600. And turns out that for polynomial corners, we have more or less the same bound. So let A be subset of FP square that does not contain the following polynomial corner. Oops, this is typo. It should be Q. And then there is no assumption on this polynomial except that the degree of our polynomial is less than P. So actually one can take the degree to be equals to P, but as long as the polynomial is not a degenerate polynomial. But for simplification, we consider Q to have degree less than P, and of course non-constant polynomial. Then we have more or less the same bound as Jabrdi-Lovett-Ostuni-Softy. So this is better compared to the integer case, because in the integer case, clearly this bound is better compared to Kravitz-Cook-Leng's bound. Okay. So before going to the proof, so our proof is similar to Kravitz-Cook-Leng's proof. So the main idea is to use what's called transference principle. So transference principle is a principle that allows you to transfer the knowledge about the linear pattern, and then you transfer it to polynomial patterns. So in this case, actually, the first transference principle is due to Ben Green, where he showed that Roth theorem is true for prime numbers. But now by Kelly-Mecca's type bound, now it's direct consequence of that. Okay, so in our transference principle, we want to consider the difference between the counting functions of linear corner in our subset and compared to the counting functions of the polynomial corner of our subset. And we hope that the difference of these two counting functions to be small. Okay, so first let me mention what happens in the integer case, and then I will tell you what's the difference between the integer case and in our finite fields case. So first, in the integer case, the first obstacle is the image of Q of Z, where Z ranges over 1 up to capital N, becomes sparser as the degree of Q. So sorry, again, it's not P, it should be Q, becomes larger. And then the reason that they need for Q to have simple integer root, they need to use Hensel's lemma to leave the polynomial to somewhere else. So for example, if you think of Q of Z as Z square, then the range over 1 up to capital N, and if you consider it as mapped from 1 up to capital N to 1 up to capital N, then it occupies only square root of N of the set. And then if you consider a higher and higher degree, then the image becomes sparser and sparser. Okay, so in the integer case, one considers the difference between the following two counting functions. So the first one is the following counting function. So let 1 sub A to be the characteristic function of the set A. So, and then we denote the capital lambda of 1A, 1A, 1A to be sum over all xy in the integers. And then we take the average over Z in N divided by some constant to the 1 over D. So the reason of this is, again, because the image of the polynomial is getting sparser and sparser of this product. So the product of 1A of x, comma y, 1A x plus qz, comma y, 1A x, comma y plus qz. So here, beta d is the coefficient of highest degree, not of q, but we shift q of z by the simple integer root. So it's q of z minus rho, with rho is the simple integer root of q. And we consider the difference of this counting function with the following counting functions for linear corners. But we need to have some weight function here. Okay, so in particular, this weight function actually depends on capital N, but we hide the notation here. And the other obstacle here, this weight function is unbounded function in terms of capital N. So that means that it's not that good, like to consider the difference between these two, but it's enough to get the result. Okay, so the last obstacle that I want to mention, similar as Ben Green's transference principle, one need to use something called the W tree. So because, for example, x squared then we know that the image should be quadratic residues of certain modulo numbers. Then in the other polynomials as well, then we need to use W trick to avoid the bias of QZ with respect to some small moduli. Okay. So that's the main idea for the integer case. So what's the difference between the integer case in the and finite field setting? In the finite field case, we don't have all of those abstractions. Okay. So one noticeable thing in the finite fields case is the image of any non-degenerate non-constant polynomial is relatively dense in the finite fields itself because the image wraps around. Unlike in the integer case, for example, if you have z square, then in the finite field case, then it occupies around p over 2. Yeah, actually, it's p plus 1 over 2. But like in the integer case, if you consider from 1 up to capital N, it occupies only square root of n of this set. Okay. And then we also modified the counting operators. So we normalize everything. So we consider the average over all x, y, z in FP. And then we don't need to modify anything on z. Unlike the integer case, again, we need to restrict it to a smaller set instead of 1 up to capital N. And similar for the lambda model. But here for the lambda model, we also don't need to consider this function multiplied by any weight. So the weight is actually only 1. So it's far more convenient to work on the finite fields setting. And then we can rewrite the following counting operators on the polynomial corners as follows. So instead of having QZ inside of the function, we can substitute it with Z. But then the weight appears on the counting operators on the polynomial corners instead of in the linear corner. So in this case, our weight function is some constant times the characteristic function of the image of Q over FP of Z. And then this constant only depends on the polynomial Q. And this is the unique constant such that the average of this function is 1. Okay. And then again, in this case, our weight here does not depend on FP. And actually, it's bounded in terms of P. Okay. So again, as I mentioned, we have that the weight is bounded in terms of P, and it's very convenient to consider the following weight compared to the integer case. Okay, so one can show that by several applications of Cauchy-Schwarz inequality, then we have the following bound. So the difference between our counting operator in the polynomial corners and the linear corners, you can bound this as U3 Gower's norm of W minus 1. So if you are not familiar or if you are familiar with this, I will recall again the definition of Gower's UK norm. So for any integer k, you can think k at least to be 2. Then for any function from definite field to complex numbers, the 2 to the k power of the UK Gower's norm of f is the average of x, h1 up to hk in FP. And then you take the product over all dyadic cubes with vertices consist only of 0 or 1. And then you have the following conjugation operator to some power absolute value of omega. So absolute value of omega, you count the number of ones in omega. And then apply to f of x plus omega dot product with h1 up to h cube. So for example, if you have even numbers of 1 as coordinates in omega, then C of f is just f itself. But if you have odd numbers of 1 in coordinates of omega, then C to the absolute value of omega of f is f conjugate of whatever inside it. Okay. So I will also mention that one popular way to get bound for Gower's norm is to use inverse theorem for the Gower's norm. And one can view this as one of the most important theorem in the modern additive combinatorics. So usually if you want to bound Gauss norm of certain function, you consider the correlation of the function with something called nil sequence. So it's a generalization of the linear phase of Fourier transform. But turns out that in our case, especially in this finite field, we can bound the Gauss-Euclidean norm without using the inverse theorem for the Gauss norm. And maybe this bound is better compared if you use the inverse theorem for Gauss norm. But turns out that we require some algebraic geometry tools to bound the Gauss-Euclidean norm directly. So I think, for example, we've known well conjectures on Riemann hypothesis for finite fields. So that gives us quantitative bounds in algebraic geometry for finite fields. And we'll use some theorem, something like that. Okay, so the following bound is called Langweil estimates. So this appears in their study of Weil conjectures, which eventually was proved by Pierre Delin. So we don't need that. We only need the following Langweil estimate. So let's say you have an affine variety over Fp of dimension n. And then let's say you have that C to be the number of irreducible components of our variety such that these irreducible components are also geometrically irreducible. That means that if we consider X as variety over algebraic closure of Fp, then these irreducible components are also irreducible there. Then we have that the number of points of X in Fp is equal to the number of irreducible, absolutely geometrical or geometrically irreducible components times p to the n plus big O of p to the n minus 1/2. Okay, so we consider our F to be W minus 1, and then we need to consider the fiber of X with respect to Q. So by Lagrange interpolation, one can find a polynomial arc with rational coefficients, and the degree of R is equal to D. So D again is the degree of our polynomial Q, such that R of 0 is equal to 0, and R of M equals to 1 for M equals 1 up to D. So the main idea to use Lagrange interpolation, then we can write our characteristic function of the image of Q over Fp as R of ln of X. So then we can write f of X as the following linear combination that comes from R. And then the idea is to fix any J. So because we want to bound U3 norm of F in terms of U3 norm of the right-hand side, and then we use triangle inequality, and we only need to consider J such that we have the U3 norm of the right-hand side is the largest. So actually you can pick any J, and then we can bound that. So here actually G depends on J, but as I mentioned, it doesn't matter what J is. You can pick your favorite J, and then write G equals to the n to the J. So this function you raise to the power of J minus mu of J. So mu of J is the average of our function n to the J. And then by triangle inequality, you can bound the U3 norm of F in terms of U3 norm of G. So the reason for this is because if we consider the U3 norm of F, there are a lot of technicalities that we should face. So to avoid that, we work with U3 norm of G. And turns out that we can write the U3 norm, the 8th power of U3 norm of G nicely as like this. Okay. So here, n sub B is the following quantity. So you can think of it as restriction of Gauss norm in subset of our dyadic cubes. Okay. And then we build the following varieties. So the following varieties comes again from the fibers of Q. So you don't need to bother with the exact definition of this, But the idea is to use double counts repeatedly and to use long while also repeatedly. We can find the quantity n sub b that appears in the last slide in terms of mu j and plus some error. So this mu j, we consider it come from CB and CJ. And then if we use double count several times and long while several times, then we get the following quantity. Okay, with this quantity, we end up with the following bound on the 8th power of utrinomes of G. So it turns out that the 8th power of utrinomes of G is big O of p to the minus 1/2. And then because of our triangle inequality, we have the following bound. And then if we take 1/8 power of both sides, then turns out that the utrinome of F is big O of p to the minus 1/16. And then because of that, if we have a subset that avoids polynomial corners, then the size should be big O of this plus big O of p to the minus 1/16. But clearly, big O of p to the minus 1/6, sorry, it should be p squared times p to the minus 1/16. But clearly, this one is less than this one, so we can absorb this error term to the following one to get our result. So I think that's all for my talk. Thank you for your attention.
Thank you very much. Are there any questions for our speaker? If not, we thank Laurence again. And Glenn, if you can upload your slides, the next talk, your talk, will be in 3 or 4 minutes.
Okay, would you like me to, should I just like screen share or?
Yes, yes.
Okay.
That's all, yes.
Okay, got it.
Everything else is beyond my pay grade. Okay, we'll just wait a couple of minutes. You're going to be somewhere in Georgia in the next academic year? Is that what I remember?
Yeah, I'll be at Georgia Tech. Mhm. Yeah. Yeah, I was gonna put my Georgia Tech affiliation on the title slides, but I haven't gotten my institutional email yet. So I figured I would just keep my undergrad affiliation for now.
Yes, so you are in some transition state. Yes, it's like
Yeah. No man's land. Yeah.
something like that. Yes.
Yeah.
Yes.
Yeah. Sorry for being late. I'm actually in I'm in Bonn right now.
You
Giving
are?
a yeah. So this is